Today we'll talk about like sort of a review of the information theoretical concepts that we need in this course. And basically I will start by this inequality, which will play like an important role in this lecture, which is that the natural logarithm of a positive alpha is always upper bounded by alpha minus 1. And basically you have equality if and only if alpha is equal to 1. And you can use this inequality to show also that len of alpha is greater than or equal to 1 minus 1 over alpha. Okay, so it will play a role here because basically many concepts in information theory are defined in terms of a logarithm, and many times we need like to have an upper bound or lower bound. Okay, so suppose that you have a discrete random variable that takes basically n values. And of course, the sum of the probabilities is 1. Okay, so P1, P2, basically this is the PMF of the random variable x. And so we define the entropy of x, h of x, as the uncertainty in x. And to measure it in bits, we use the logarithm to the base 2. And this is like the master equation. Okay, which is that if you have a discrete random variable that takes n values, then h of x is summation k from 1 to n. And then we take pk, which is the probability that x is k, or takes the kth value, x kth. And then the logarithm to the base to 1 over pk. So you can write down this summation as an expectation, right? Because you are taking a function here, and you are basically multiplying the function by the respective probability and then doing a sum. So this in fact is an expectation, and so this is the expectation of minus log 2 pk. Okay, so basically in this, if you see something like this, then it means that you will multiply by the PMF and sum, and so you get this summation here. Probabilities, the probability is something that is less than 1, the logarithm is negative, and so with the minus sign here you get something that is non-negative. And so like if you want to measure the entropy in bits, then again use the logarithm to the base 2. If you want to measure it in nats, you use basically the natural logarithm to the base e. And sometimes, I mean, you know, this thing is not like, you know, is not, you know, as conceptually straightforward as this, you know, bits, but it makes like life easy because like if you use the logarithm to the base 2 and then like you're doing you know, you take the derivative and stuff like this, then you have those factors len 2, len 2, len 2, and sometimes it's basically like more convenient just to use the logarithm to the base e. Okay, but anyway, both are fine, and using to the base 2 is not that problematic. It's just, you know, it has those annoying factors of len 2. Okay. When, of course, like, you know, if you know, suppose that there are values, you know, so here I took the values to be positive. If there are values that for the probability that are equal to 0, then you can check that this limit is actually equal to 0. Okay, so you know, this thing, you know, here, you know, if I write it without a limit, then it is to be understood that there is a limiting operation and that this is equal to 0. You can check that basically the function, this function h of x, you can think of this h of x entropy as a function of those probabilities, which are b1, b2 up to bn. And you can check, you know, using the second derivative or using even the main definition of concavity, that actually this function, you know, is a concave function of those variables here. And this may be important, like if you are involving the entropy in an optimization problem or something like that, and you want to investigate whether your objective function or one of the constraints is a convex or concave function. Okay, so this is like sort of like a definition. Okay, so you can think of this as a definition here. Okay, and what are the properties? So if you define the entropy to be something like this, what are the properties? And of course, there are so many properties, and I will focus on those that are relevant to us here. Okay, so first one. So here is like our first serious business. Take h of x minus log n to the base 2. So again, the discrete random variable till now is assumed to take a finite number of values, and specifically big N values. Now, if the discrete random variable is uniform, right? So if it's uniform, okay, so if x is uniform, it means that this probability bk is equal to 1 over n for every k. And so if you apply the formula will be summation k from 1 to n, okay, and then you have bk, which is 1 over n, and then you have log 2n. And so log 2n is, you can take it as a common factor, and then and also 1 over n, and then you sum 1's n times, 1 plus 1 plus 1 n times, so this will give you an n, and n goes with an n, so you end up with this log n to the base 2. So log n to the base 2, I mean, what is doing here, it's like this is the entropy of a uniform x. Okay, so so we are interested here in comparing the a general entropy with the entropy of what if the random variable is uniform. Okay, so it has n values to take, and it takes them with equal probability. Okay, so what you can do is write down the formula for h of x, and then for this log n to the base 2, you insert this summation here, which is equal to 1 because it's a PMF, and then you combine the two guys, you combine the two sums, and so that you will have a logarithm, and you can basically write it as a single logarithm, log 1 over bkn to the base 2, and then then comes the rule of the inequality. And because the inequality is mainly for the natural logarithm, so this is, so basically you change this into a natural logarithm by dividing by the ln of 2. So that's the annoying thing about using the logarithm to the base 2, but it's fine. And then the natural logarithm itself is upper bounded by this quantity minus 1. Okay, so this will be, so you have a factor 1 over ln 2, and then you upper bound by this quantity minus 1. And then you have a sum here, which will give you bk will go with bk, and then you sum k from 1 to n, 1 over n, and so this will again will give you n over n, which is 1, and then minus a summation of the probabilities, which is also 1, so this is 0. So that's very nice, because it tells you that h of x is always less than or equal to, so an upper bound on the entropy is log n to the base 2. Okay, so it means that among the discrete random variables, taking n values, the one with the most entropy, okay, is basically the uniform guy. Okay, so it's an upper bound on any basically on any entropy, and we are sure about this. There is no other distribution, because remember that actually our inequality that we used here, this inequality comes with an if and only if condition for equality. So you get equality if and only if basically this is equal to 1. Okay, if this guy here is equal to 1 and this guy is equal to 1, if and only if bk is equal to 1 over n. Okay, so this is so entropy basically its maximum for discrete random variables that take a finite number of values whenever the discrete random variable is uniform. Okay, once you deviate from uniformity, then the entropy is lowered. In this course and in this lecture, I am not talking about why actually the entropy is defined as such. I leave this to you can read it in an information theoretical book. This expression here is motivated, and it can be sort of obtained axiomatically by basically saying that I want to define the information content in a random variable such that it has so and so properties, and then you actually show that this is your function. Okay, but this is a long story, and again, here I won't focus on basically using this expression. But of course, there is a big and very nice story behind this expression itself. Okay, so here we are, we are being superficial, and we are taking like this for granted, and that this is sort of a very nice measure of the information content of a random variable. And now we know this piece of information, which I'm sure like you also know from a previous course. Typically, like people studying digital communications also teach this inequality, that the entropy is maximized when you have a uniform random variable. Okay, so typically in communication channels we have at least two variables. Basically, you have the input to the channel and the output from the channel, and so we are interested like in having like stuff that is related to two or more random variables. So let's start with the notion of a conditional entropy. Okay, so conditional entropy is basically, you define it in two steps. So first, you have another random variable y, and you condition y on small y. So you say that big Y takes a specific value, okay, and then you define the entropy. You will find that the expression is like the expression above, but it has, rather than the probability of x equals something, it is conditioned on y, okay. So now if you take the average, okay, so this thing here is basically that you take this and you say, okay, I will average over y, okay, because big Y itself is a random variable, so it takes those values. So if you average over y, you have this quantity here, again, which will be very important to us. It's the conditional entropy of x given y. It's the uncertainty in x given y. So if you know y, what is the uncertainty in x? And using the PMF of y, you can basically write down this expectation here, and you will get that the formula for the conditional entropy is basically this double sum that involves here the joint PMF of x and y. So this is the joint PMF. And then the logarithm will be applied to the conditional, basically PMF of x given y. Now you can show that actually h of x given y is less than or equal to h of x, and so the meaning is straightforward. The meaning is so if h of x, this thing, is the uncertainty about x, then if you observe y, so suppose that you have access to an observation or a measurement, then what happens regarding your basically uncertainty about x? Your uncertainty about x will remain the same, or it will actually be reduced by observing y, right? So when I say that the entropy of x given y is less than or equal to the entropy of x, I'm saying that you go and observe y. Well, the worst case is if x and y are independent. In that situation, knowing y tells you nothing about x, and so the entropy of x given y will exactly be equal to the entropy of x. The uncertainty in x remains the same because you went and measured something that is independent of x. But if x and y are dependent, then definitely when you measure y, you know y, this will tell you something about x, and so the uncertainty in x will drop, will go down, and so h of x given y is less than or equal to h of x. Okay, so this is like sort of like something, a property that you want, and the entropy, the formula for the entropy that we take for granted actually guarantees that this is the case. Okay, and to show it again, our friend now is this logarithmic inequality. Just take the conditional entropy minus the entropy. Okay, and so this guy again is summation x and summation y. This is b of xy, the joint log 1 over bx given y. And this h of x here, is basically summation x, b of x log 1 over b of x. Okay, and the trick to combine these two sums into a single sum, as I did here, is simply to rewrite the PMF of x using the joint, right? So we know from the law of total probability that the PMF of x itself is summation over y, the joint of x and y, right? And so now this thing is a double sum x and y, b of x comma y, log 1 over bx, and this will allow us to basically combine these two double sums, and then what? Then just employ this inequality here, which will tell you that basically you get a 0. So it's always the case that h of x given y is upper bounded by h of x. Okay, any question? Okay, joint entropy, it's h of x and y, and it's defined using the joint here and there. Okay, so that's the joint. And you can show that h of x given y, okay, so this is very important, h of x, h of x and y, h of x and y, so that's the joint, is h of x plus, not h of y, h of y given x, or it is equal to h of y plus h of x given y. Okay, so you can write it this way and this way. And again, to check something like this, very straightforward. Take the expression for those guys and add them. And when you add them, you will be able to combine the logarithms and basically get a double sum in which you have the joint PMF here and the joint PMF there. Okay, so h of x and y is basically, you can write it, and it depends on what is needed in your derivation or something like this. H of x comma y is, so the uncertainty about two random variables x and y, it's the uncertainty in x plus the uncertainty of y given x, or it's the uncertainty in y plus the uncertainty of x given y. Okay. So now, this is h of x comma y. Now, how does this thing is compared with h of x? Well, h of x comma y is equal to h of x and then an entropy. For discrete random variables, the entropy is non-negative. So this is non-negative, okay, for discrete random variables. And, you know, basically, the main definition of entropy is applied to discrete random variables. So basically, h of x comma y, the joint, must be greater than or equal to h of x. Okay, because the difference between them is a non-negative term, which is the conditional entropy of y given x. But from the previous slide, we said that basically, you know, this guy itself is upper, you know, the conditional entropy is upper bounded by the entropy, the unconditional entropy. Okay, and this one will be upper bounded by h of x. So what you can do is that you can upper bound this term by h of y, and so the sum of the two entropies is an upper bound on the joint. Okay, and so when is this inequality satisfied with equality? So when the uncertainty in x and y is the sum of the uncertainty in x plus the uncertainty of y. So how is this satisfied with equality? Independent, yes, exactly, yes, independence. Because independence, you know, is, you know, so basically this inequality, it comes from basically the inequality that the conditional entropy is less than or equal to the entropy itself. So once you have independence, you have equality in, you know, regarding the conditional entropy, and so this will be reflected here. So you have equality if you have independence. No, so it's no, because basically it is, you know, it is not, you know, this is h of x. It's not h of x plus h of y and then we upper bound it. The problem is that this is the sum h of x, h of y given x. H of y given, it's not h of y. It's h of y given x. Okay. Now, if you have independence, then what you wrote down is correct, right? Because if you have independence, then the joint entropy is the sum, and the sum of these two non-negative quantities is definitely lower bounded by basically any of these guys, or basically by their maximum. Okay, so your inequality is true if we are talking about independence, but generally things are complicated like this. Okay, so how can we get this one satisfied with equality? This one. again, just use the intuitive meaning of uncertainty. So how can it be that the uncertainty regarding x and y is exactly the same as the uncertainty regarding x? Okay, can you think of a situation? Y is fixed. Okay, so yeah, generally, if y is basically is a one-to-one function, you know, a bijective function on x, right? So if y, okay, so suppose that if y, you know, so if y is fixed, that's one situation, okay. So if y is equal to g of x, right? And actually, you just need, just need to be a function because if it's just a function of x, okay, it means the following. It means that once you know x, so that I mean here by the function, it's a known function. So once you know x, then you can compute y, and so the uncertainty about y is basically will be equal to 0. So h of g of x given x, this is equal to 0. Okay. You don't need to impose anything on the function here. You need to impose it if you want to do the other way, which is h of x given g of x. But like in this way, again, the idea here is that suppose that the random variable y is just a transformation of x. So if you know x, there is some deterministic function you give x to and you get y. So in that case, once you know x, you definitely can compute y. Okay, and so in that case, the joint entropy in x and y will be basically the entropy of x. Now, the mutual information is the amount of, it's basically the difference. So it's h of x minus h of x given y, or h of y minus h of y given x. So if we go to the upper line here, so h of x, uncertainty about x. H of x given y, uncertainty about x, the uncertainty remaining in x if you observe y. So what is the difference between these two guys? Oh, so the difference will be the uncertainty about x removed by observing y, or it is the amount of information about x revealed by observing y. Okay, so mutual information, which is written like this, ix semicolon y, basically it is the information revealed about x by observing y. And you can see that if x and y are independent, then h of x given y is h of x, and the difference will be 0, which means that there is no information revealed about x by observing y if x and y happen to be independent. Again, each one of those guys, it has a definition in terms of the summation, and the PMFs and so on, and you can plug in the expression, and this is the expression for the mutual information. It's a double sum, and here you have the joint PMF, here you have the joint PMF, and here you have the PMF of x, here you have the PMF of y. Okay. Now, many random variables of interest in communications are actually continuous. So, so perhaps, if we're talking about bits and so on, the messages, we can talk about discrete random variables, but, by the end of the day, the signal, you will have this annoying additive white Gaussian noise in the receiver electronics. So what about continuous random variables? So let's give this an attempt, which is, whenever you have something discrete and you try to think about, going to continuous, like maybe try to have something like a Riemann sum or something like that. So this is exactly what we'll do. So suppose that x is a continuous random variable, and basically, you basically take the axis and divide it. Okay, you say that probably, sorry, if you have a continuous random variable, so you have a continuous random variable, you say, well, we don't know about the continuous random variable, but we can generate a discrete random variable, okay, and the discrete random variable will be, you will discretize, okay, and, you basically take those here, okay, so you say, well, the probability that x is equal to k delta, and so delta is the separation, is, it should be like x equal k delta, Now again, like for a continuous random variable, the probability that x is equal to a specific value is 0, right? It's 0. And actually, if by definition, if the probability that x equals any subset of R of low big measure 0, the probability will exactly be 0. So the probability that x is like a rational number is also equal to 0. But here what you say, okay, we will discretize, we will write down, so now we will take a delta that is positive, and we will say that the probability that x is equal to k delta. Okay, so you start, you take your axis here, and you again chop it off like into intervals of equal length, which is delta 0, delta 2, delta 3, delta, and minus delta, minus 2 delta, and then you say, well, the probability that x is equal to k delta is the PDF, because our random variable is continuous, so it has a PDF, if f of x k delta multiplied by delta approximately. Okay, and so we will say that this is very close to the truth if delta gets smaller and smaller and smaller. Okay, so delta is positive, and we can imagine that it is infinitesimally small. Okay, so this is like sort of creating a discrete random variable from the continuous random variable, because for discrete random variable we know how to define the entropy. Okay, at least we took this expression for granted, so you just put the probability, so it is minus the summation, and then you have the probabilities here. Okay, and then the logarithm. Okay, and then of course, like there is like something that I didn't talk about, which is I started by talking about discrete random variables that take finite values. What about infinite values? Is the entropy defined? Well, it is defined, but for some random variables, but for some other random variables, the summation for the entropy, if the random variable is like, say, takes an infinite number of values, and we have discrete random variables that may take the values, for example, the natural numbers. So for those, sometimes the summation for the entropy may explode. Okay. So once you go to infinity, perhaps some random variables will have like an infinite entropy. But here again, like we will just assume that yes, we can take our discrete random variable can take all those values, 0 plus or minus lambda plus or minus 2 lambda and so on, plug in the approximate probability, which comes by doing this approximation, and then do the logarithm. Okay. And then this will be you basically have this logarithm of these two guys multiplied together. Then you can split the logarithm of the product as the sum of the two logarithms, and you get two expressions here, like 1 and 2. Okay, let's see. What about the first one here? So the first one here, it looks like you can take it back into an integral, right? So basically, this is a summation of a function. It's like a summation, and then you have some function k of delta multiplied by delta, right? And then k is in z. So assuming that actually you have convergence, okay, then this thing, as delta gets very small, it's a Riemann sum, and this thing is like integral from minus infinity to infinity, psi of x dx. Okay, so again, we have a function here that you take the value of the function every k, k delta, and then you multiply by delta. So if you think about this, it's like having those the areas of the rectangles under the curve, and this is like sort of a Riemann sum. And assuming that actually it converges as delta goes to 0, then you have an integral. And so this integral will be this integral that is written down here. Okay, so this is the guy. But there is another term. Okay, let's look to the other term, and let's see what happens if we take the limit as delta goes to 0. Now this guy is sort of nice. It's the same story here, and so this will sort of like converge to integral minus infinity to infinity f of x dx. Well, that's 1. But then we have this guy here, log delta itself, and if you take the limit as delta goes to 0, so basically limit delta goes to 0 log 2 delta, this is minus infinity. Okay, and so with the minus sign here, you get an infinity. Okay, so the idea is like the information content of a continuous random variable is like infinite. Okay, so it's like, you can think of it like, that the continuous random, let's say Gaussian, if you generate, not on a computer, like in a hypothetical world in which like you can have actually things with infinite precision, well, a real number, it's expressible in an infinite number of bits. So you expect that continuous random variables will have this, annoying property that basically, their entropy is infinity. Right, because like once you do a measurement and get a value for a Gaussian random variable, it's a real number. Okay, it's a real number, and again on a digital computer, it's not really a real number. It is quantized. It's using the 64-bit IEEE format and so on. But like in a hypothetical universe, this is like sort of if you deal with real numbers like as if they are true. Then basically you have an infinite amount of information. So that's annoying. So what should we do? Should we like just restrict the definition of entropy to discrete random variables? No. So here is basically what people ended up doing. They said, okay, but what about the first term? The first term is like looks nice. It looks like the entropy of a discrete random variable. With the summation turn it into an integral. Like for the discrete random variable, it is b of x log minus 1 over b of x. And here we have a PMF. Here it's like a PDF. And for many random variables of interest, if you actually do this integral, it will give you a finite result. So it converges and everything. So we will just deal with this guy. Okay, and officially speaking, this quantity here, again, like for a continuous random variable, if you go for entropy, it's infinity. It is infinity. And so you say, well, this quantity here is like sort of common. It's common to all continuous random variables. Okay, because again, this quantity is 1. Okay, so there is a summation here that basically is the integral of the PDF, which is 1. And so you have this quantity, it's common. So regardless of the distribution, you will get always this quantity here, which is minus log delta to the base 2. And so you get this infinity in all of them. So just ignore it and talk about this quantity. And this quantity will be given a name, differential entropy. So for continuous random variables, we use differential entropy rather than entropy. Now, differential entropy is, is something that, like, for many random variables of interest, is finite, manageable, and everything. In this course, okay, because like information theoretically, we will be very superficial. I will not basically pay a very, big attention to the difference between differential entropy and entropy. Okay, so I will just entropy, and you understand that basically, if we are talking about continuous random variables, then you know basically the story that in front of your eyes right now, and that actually it's differential entropy and so on. The nice thing is that many properties of entropy are inherited by differential entropy. So many of the properties, the useful properties, are basically there in differential entropy. And so the difference is not that big. But for example, one difference is that differential entropy can be negative. Differential entropy can be negative. Okay, so there is no guarantee. There is no guarantee here that this thing here, if you evaluate it, you will get a strictly positive result. Okay, but otherwise, like especially if you start like doing conditioning and so on, many properties are preserved. Okay, so in this course, again, I warn that we will not be rigorous. Sometimes the entropy, I may be referring to the additive white Gaussian noise, but I will just use entropy. Okay, so we will just have this way. So it's as if for users of information theory, it's like basically that it's like this sum is changed into an integral, the PMF is changed into a PDF, but of course there's a story there. Okay, and typically the differential entropy is denoted by small h. Same story. Sometimes I will write the entropy of a continuous random variable with big H. Differential entropy can be negative. But for example, if you start doing this same game of converting sums into integrals, PMFs into PDFs, if you study mutual information will always be non-negative. So even if you define it in, for basically continuous random variables. Okay. Suppose that you have a random variable A. It goes, it goes, let's say, through a channel, because this is what we are used to in wireless communications or communications in general. So if A goes through a system, okay, here I'm just using channel again because it's a communications course, and then you get B, and then B goes to another channel, and then you get C. Then there is something called the data processing inequality. And the data processing inequality tells you that the mutual information between A and B is greater than or equal to the mutual information between A and C. And the mutual information between B and C is greater than or equal to the mutual information between A and C. So the moral of the story is you basically, you get more, you have degraded information if you go through like a cascade of channels. Okay, so like you can think like each channel is like, is causing its own troubles. Okay, so again, this is, very important to keep in mind that the mutual entropy of A and B, so see, A and B, between them is just one channel, is greater than or equal to the mutual information between A and C. Okay, and basically the mutual information between B and C is greater than or equal to the mutual information between A and C. And to prove something like this, exactly, we need an assumption, and this is the assumption. Okay, so let's put it here. The probability of C, B, and A. So the probability of C given B and A is equal to the probability of C given B. So in words, what does this mean? So the probability of C given B and A, C given B and A, is the probability of C given B. So A and C are, A and C are what? No, not independent. So A and C are what? They are conditionally independent given B. Okay, you can come up with examples, okay, in which this is true, but for example, B of C given A is not equal to B of C. Okay, so not necessarily true. Okay, so this is this is something important to keep in mind, that sometimes basically two random variables are conditionally independent. So given some third random variable B, in this case they are independent. So are they independent? Perhaps yes, but not guaranteed. And again, like it's like in introductory courses on probability, it's like a typical thing like to give this counter example in which like two random variables are conditionally independent given a third random variable, but but they are actually dependent. Okay, so here the way to say it, to be valid like sort of universally, that if you have basically an expression as such, it means that C and A are conditionally independent given B. Okay, so what is another description of A to B to C? So these three random variables also they have a name, like you have this property that given B, A and C are independent. Memoryless, okay, or you can say that this is A, for those who took 241, it's Markov chain, but it's a Markov chain. Okay, so basically given B, so that's actually a Markov process, a random process is Markovian. So basically if we imagine that the process like is in time, we say that basically for a Markov process, the future and the past are conditionally independent given the present. Okay, so here we are talking about like things in terms of time, but the definition is generally valid for any even abstract random variables. Okay, so if you have like so A gives B, B gives C, because B is A processed by channel 1, C is B processed by channel 2. But if you have this property that C, that C and A are independent given B, that's the Markovian. That's exactly the Markovian property. Okay, and so anyways, keep this in mind. You will need this, so you need this condition here. And again, how do you remember it? You remember that the mutual information between two random variables separated by one channel is greater than or equal to the mutual information between two random variables separated by two channels or more even. Okay, so that's the data processing inequality. Something else that is very nice, and again, I am writing here things in terms of big H, but it's also, and that's the nice thing, also applicable to differential entropy, which is called translation invariance. So translation invariance, it tells you, basically if you take a random variable and you shift it, so you take the values of a random variable and just add a constant, well, the entropy is the same. What may be more interesting is that the conditional entropy, if you add a function of the random variable you are conditioning on. So suppose you have the entropy of x given 1. Now suppose that you take x and you add to it a function of the random variable y on which you are basically conditioning, then guess what? Entropy is stubborn, exactly the same. Okay, I'm writing here big H, but again, we are not rigorous. You can replace big H by small h. So this is for any type of random variable. And this is very useful as you will see in the remaining part of the lecture. Okay, so translation invariance is again this property that if you are conditioned, if you add a constant to your random variable, its entropy remains the same. And if you are talking about conditional entropy, if you add a function of the random variable you are conditioning on, then you have the same entropy. Okay. And this adding of a constant, okay, again, the general rule, adding a constant to x is a bijective function. Do you agree? Right? So the function, x, it takes x to x plus a. It's an invertible function. It takes every x to some x plus a and vice versa. It's a bijective function, right? So actually, this property is for any bijective function. Okay, so again, the way to show it quickly that the joint entropy of x and psi of x, where psi is some deterministic known function. On the one hand, it is h of x plus h of psi of x given x. Right, so that's one definition of joint entropy. It's the joint entropy the entropy of this guy plus the entropy of this guy given x. And like I said before, in the lecture, that basically knowing x, the entropy of psi of x given x is 0, because once you know x, you have no uncertainty regarding psi of x. If x is known, x is 7, go and compute psi of 7. That's it. You will get a number, and you are very sure about it. I mean, there is no residual uncertainty or anything. So this will be 0. So basically, this joint entropy is equal to h of x. But there is another formula for the joint entropy. You can write it as the entropy of psi of x plus the entropy of x given psi of x. Okay, so this entropy here is greater than or equal to 0, as and basically, is it 0? So here is the question: is this thing guaranteed to be 0? So this thing is guaranteed to be 0. What about this one? Guaranteed to be 0? No, right? Because suppose that the function psi is a square, right? So you suppose that psi of x is 4. You still don't know whether x is 2 or minus 2, right? Stuff like this, right? Not all functions. If I give you the function, but if the function, if you are talking about a function that is injective, okay, then that's it. Basically knowing psi of x will tell you exactly what x is. So for those functions, you can say that this is equal to 0, and you will have this satisfied with equality. But generally, it is an inequality. So the entropy of a function of x is less than or equal to the entropy of X, with equality if this function is invertible. Okay, and so it's like this one here. So this is like sort of a generalization of this rule, and again, very useful as we will see. Okay, now basically we reached one of the very useful theorems that we'll make use of in this course, which is suppose that you have random variables, okay, and actually let's go for random vectors. Okay, you know, so basically h of x comma y is, you can think of it as the entropy of a random vector, you know, x and y, and you can extend it to many random variables. Okay, what you will do is that, you know, in your expression, the joint PMF or joint PDF will be like of those random variables. So suppose that again that you have a random vector, and this random vector actually is constrained to have a certain covariance matrix. Okay, and then you ask yourself, what is the distribution of the random vector with a given covariance that has the maximum entropy? Okay, again, if we are doing this for, actually we are doing it for continuous random variables, but again, I will not, like, again, go back and forth between entropy and differential entropy. I will just say this thing, okay? So we want to, what is the distribution given a covariance matrix? So basically the covariance matrix is fixed, which, like, in communications, the meaning of fixing the covariance matrix is like, you know, is like you are fixing the total transmitted power. If you have like multiple antennas or multiple channels, then you are fixing the total transmitted power, which makes sense in communications. Like we typically have those power constraints, as we'll see. Okay, so given a covariance matrix, which guy among the distributions we know of, which guy actually has the maximum entropy? Okay, it turns out the Gaussian. Okay, so the Gaussian has this very nice, very nice property. And if we are talking about, like, you know, vectors, random vectors that, you know, that are complex valued, then actually it is the circularly symmetric Gaussian. Okay, how can we prove something like this? Okay, so first, I mean, we can use the expression. You know, we can use the definition of, you know, of the differential entropy, right? So again, remember that the differential entropy of a random variable, which, you know, I just put it, h of x is minus f of x log 2 f of x dx. So if you know the PDF of the Gaussian distribution, you can just evaluate this integral here, and this is the result that you will get. Okay, this is the result that you will get. Okay, so the special case in which, like, your random vector is just one single random variable, you'll get this result here. The entropy is log to the base 2 pi e sigma squared. Log to the base 2 pi e sigma squared, where sigma squared is the variance. You know, there is no dependence on the mean value, right? And this is expected or not. So the entropy here does not depend on the mean. Is this something that we expect? Yes, translation invariance, right? Because any non-zero mean random vector, right? You can basically you know, you can think of it as a constant vector with the mean, and then another basically zero mean random vector, right? But the relation is, if you have a random vector and a random vector to which you add, you know, you add a constant vector, well, by translation invariance, the entropy is exactly the same. Okay, so basically we will not bother about means and so on, you know, because again, shifts do not change entropy. Okay, so now let's go again to this very fundamental result to our purposes, which is you know, which is this business of fixing a covariance matrix and saying which among the distributions give us basically the maximum entropy. Okay, so you can solve this problem using calculus of variations. Not that basically your optimization problem is a bit like you know, it's not that straightforward, like, because like your unknown is the PDF itself. It's like you are asking, you know, you want to maximize this guy here, you want to maximize this guy here, okay? Subject to, okay, so subject to, so for scalars, you want basically this is given constant, okay? And for vectors, you want basically the covariance, the full covariance matrix to be like sort of specified, okay? And so what is your unknown? All right. So functions that are non-negative and that integrate, okay, so there is another constraint, of course, that is a PDF, it's one. Okay. So again, this is a problem. It's called calculus of variations because your unknown is basically this one, and we will come back to, we will deal with calculus of variations when we solve the power control problem. For now, I'll actually do something that is more satisfactory, like in terms like, because again, calculus of variations, it has like so many assumptions actually to work. Here things are, I will just use inequalities. Okay, sometimes using inequalities to solve optimization problems is the way to go, and it tells you everything in a justified way. But these frameworks, again, they are like, you need like conditions and so on. Okay, so we'll go for this. In some, I'm telling you this because like in some references, basically they just go for basically this optimization problem. What I'm doing here is the following. I will take the entropy. Okay, and again, I'm writing a big H. Okay, so we know the story now. The trick is this is the definition of the entropy. I will insert g of x. So what is g of x? It's the Gaussian PDF. It is the Gaussian PDF. Okay, so I will basically have it here, and of course it's not there in the definition of h of x, so I will have it there. Okay, so random variable x, it has a PDF f. Okay, and again it has an entropy that depends on f, and so I will basically insert the g, which is the the PDF of c. Okay, cn, and then 0 vector. Okay, and we won't care about the mean, right? The mean can be anything because of translation invariance, and then on. Okay, and so what we'll do now is we will upper bound. So the idea is to solve an optimization problem using inequalities is to upper bound and then show that the upper bound is achievable. Okay, so we want to upper bound. So we actually have two terms. Okay, so let's see the two terms. So this is the first term. So I will take this term here, and I will say that this is equal to the expectation using the PDF f of log 2 g of x. I will basically take the minus sign and write things as such. Okay, and so this is the integral. Okay, so let me like do it in slow motion. So this is the integral. We are doing the expectation with respect to the PDF f. So f of x, and then log 2 g of x over f of x dx. Okay. Again, we are basically even doing things for continuous random variables. Again, this is like very related to the business of the additive white Gaussian noise, and so we are interested actually in continuous random variables. I write basically the expectation as an integral here so that you can like imagine what is this expectation, and then the next order of business is basically to convert this log 2 into log to the base e, and so you have to divide by ln 2, and then to apply our friend from the beginning of the lecture, which is then alpha is less than or equal to alpha minus 1. And once you do so, you will get basically get the PDF multiplied by g over f minus 1, and then two terms. One of them will be the integral of f. Well, f is a PDF, so its integration is 1, and the other integral. One of them. When you eliminate these two guys, you will get an integral with respect to g. And g is a PDF, so its integral is 1. And minus 1 multiplied by f, it will gives you, again, another 1. And so you get 1 minus 1. So one of them is the integral of g. One of them is the integral of f. Both are PDFs, actually. And so both integrals are equal to 1, and the difference is 0. So this term here is upper bounded by 0. Before moving to the other term, again, because here we are not upper bounding for the sake of upper bounding. We are upper bounding for the sake of solving an optimization problem, a maximization problem. So a very important point is this upper bound achievable? Well, we obtain the upper bound using the inequality that ln alpha is less than or equal to alpha minus 1. And this inequality is nice. It tells you, yes, this inequality is true, this inequality is satisfied with the strict equality if and only if basically the argument is equal to 1. So basically this thing is equal to 1, which means that f is equal to g. So if f is equal to g, actually this 0 here, which is the upper bound, is satisfied with equality. Okay, so keep this in mind. But we are not done yet because there is another basically term that is here. And for the other term, actually what we will do for the other term, we will not upper bound it. Actually, we are able to like sort of evaluate it. Okay, so here is the story. So you want basically to take the expectation of log 2 g of x, and you notice g of x is the PDF, the Gaussian PDF. And so again, this annoying len 2 I talked about at the beginning of the lecture, okay, because like you need first to change this logarithm to the base 2 to len, and then take the len of the Gaussian of g of x. Okay, so when you take the len of g of x, you get two terms. Okay, so you get two terms. So this is with a minus sign. You get basically this guy here, and then you get this constant. It will appear here. Well, this thing here is like, it's a constant, like, its expectation is itself. Why is this? Because again, we are solving the optimization problem given R. So we are saying, okay, so we are hunting for the distribution, yes, but whatever distribution we get from this optimization problem, it must have a covariance matrix basically that is given by R. So R is given, and so basically this is like a constant. What about this guy here? Okay, so what is, so let me focus this part alone. So what is the expectation of x Hermitian R inverse x? Okay, how can we evaluate something like this? So the trick, is the following, and again, like you will use it a lot in this course. So you have expectation x Hermitian R inverse x. Well, if we can only get this x there, right? Because like the expectation of x Hermitian is R. The expectation of x Hermitian is R. And so if we can just put this x here, of course, I mean I cannot just do this x here because x Hermitian R inverse x is a scalar. But if you move x to the other side, you will get an n by n matrix. So the trick here is the following: equals trace x Hermitian R inverse x, right? Because the trace of a scalar, think of the scalar as a 1 by 1 matrix. So the trace of the scalar is the scalar itself. So basically this is exactly equal to that. And now for the trace, we have this extremely nice property. The trace of phi psi is equal to the trace of psi phi, given if this is like m by n, this is n by m. Okay, so the trace, you can interchange this order and you get the same trace. So this will do the step for us. So basically this is expectation of trace, and now we have x Hermitian R inverse, like this. Okay. Now, expectation and trace are, you can interchange them. Why? Because what is trace? Okay, so what is the expectation of a matrix? We mean element-wise. So basically, if you take the expectation of a matrix, it means that you apply expectation to every element. And then if you take the trace, then you will sum, the expectations of, the main diagonal elements. But you get the exact same result. You get the exact same result if you take the trace first and you sum the main diagonal elements and then apply expectation, because expectation is a linear operator. And so basically interchanging these two guys is valid so long as we are talking about finite dimensional matrices. Okay, so basically this is equal to the trace of expectation x Hermitian R inverse, and this one is R by design. Okay, we design things to be R. Okay, we want it to be R, and then R multiplied by R inverse, this will give you identity. So this in by n, and so this trace is equal to n. Okay, so this is very nice. Okay, so this result here is equal to n, and again, those steps, do them yourself, and make sure that you are, you understand what's going on here, because those are very useful. very, very useful. This trick again is like used a lot, you know, especially when we start, you know, minus systems and so on. We will have like random vectors, and again, we will have like we want expectations of things that look like this, and we say, oh, what we just want x remission so that we can basically insert in the covariance matrix. And the way to go is simply to insert this trace, a trace of a scalar in the scalar itself, use the property that trace of phi psi, and then use the fact that trace, you know, traces the sum of the main diagonal elements, and expectation is just a linear operator. You know, expectation of a sum of random variables is the sum of expectations. So this is true even if the random variables are dependent. Okay, so expectation is linear. Period. Okay, so in that case, you know, this term here, actually we were able to evaluate. This was evaluated exactly, and now you know, this is the remainder. So now what we did, like as a summary, we took the basically the entropy, okay, the formula. We inserted g of x, which is the PDF, the Gaussian PDF. Okay, and then we split into two terms. One term was upper bounded using the inequality that len alpha is less than or equal to alpha minus 1, and the other term, actually we were able to get it exactly. And so an upper bound on the entropy given a covariance matrix, okay, is basically this thing. And again, like if you say, well, I mean, why you put x Hermitian, why you put x Hermitian as the covariance matrix? I mean, perhaps x has a mean value. Always remember translation invariance. Translation invariance, it tells you that, you know, basically you can, without loss of generality, deal with vectors x that are zero mean, right? So here, like if you put things like this, I can just put this constraint also, you know, that x f of x dx is equal to 0. Not a problem, right? Because again, if it's not, I mean, no problem. The entropy actually is the same. So here it's like, you know, perhaps I need like to write it. So take expectation x equals 0 and 1 without loss of generality. Okay, again, because of translation invariance. Okay, so we have an upper bound. The nice thing is that this upper bound was achieved by using just one inequality. We haven't used anything else. One inequality, len alpha less than or equal to alpha minus 1, and it's achieved with equality if and only if alpha is 1, which in our case here is that g is equal to f, or actually more accurately, f is equal to the given g. Okay, so basically, if you have an n-dimensional complex valued random vector with a given covariance, and you ask yourself, I mean, what is the distribution that has the maximum entropy? Okay, well, it is Gaussian. Okay, so in this lecture we have encountered actually two maximization problems regarding entropy. Both are important, by the way. So one of them is related to discrete random variables that take a finite number of values. So in that case, if I tell you what is, you know, so we have a discrete random variable that can take big N values. What is the maximum entropy possible? It's log n to the base 2. It's log n to the base 2, and it's achieved by the discrete uniform distribution. Now, another optimization problem that is very relevant to communications is, now we have random variables, and then you think of them as continuous random variables, and now it's not just that we want to maximize the entropy. We want to maximize the entropy given a constraint on the second moment. Okay, you know, so if this is a scalar, you know, we are basically constraining the second moment or the variance. Generally, I mean, we will just go for a random vector. We want a constraint on the covariance matrix. Okay, so what is basically our hero now? Our hero is the Gaussian distribution. Okay, so it's discrete uniform. If you are talking about the first problem, now it is Gaussian. And again, both are worthy of being always remembered. Okay, any question? Okay, capacity. Okay, so which is like foundational, and in this course, like we will compute probabilities of error, and we will use capacity also. Okay, so Let's focus first on the SISO AWGN channel. So SISO, everything is scalar, and this is our model. Okay, so we use symbols that are 0, meaning the variance is 1, the noise is Cn0, 1, x and epsilon are independent, and there is no channel here. So I am assuming that the channel has a constant gain that is equal to 1. So that's an AWGN channel. Okay, so this is very important. Like in communications, what is the objective? What is the abstract objective? Like you have a channel, you send a message, X, you get Y, at the other side of the channel, at the receive side, okay, and you want Y to convey to you basically maximum information regarding X. Okay, so you want the maximum information you can obtain regarding X. So in communications, theoretically, we try to basically find situations in which the mutual information between X and Y is maximized. That's the essence of the so-called channel capacity. So you have a mutual information of X and Y. You say, okay, I want this thing to be maximum because, what is mutual information? Informally. Informally, mutual information is the amount of information revealed about X by observing Y. So in a communication system, we transmit X, we give X as an input to the channel, we get Y, okay, and then we ask ourselves, I want actually Y to reveal, as much information as possible regarding X. So what is the mutual information between X and Y? Well, it has a formula. So it is the uncertainty about Y, the entropy of Y minus the entropy of Y given X. Okay. Now let's start using our properties. So now this is entropy of Y given X. The entropy remains exactly the same if we shift this Y by a function of the random variable we are conditioning on. That's translation invariance. So h of y minus square root SNR x. So you can basically insert this thing here, and you have an equality because this thing here is just a function of the variable you are conditioning on. And what is this? So what is basically this y minus square root? This is actually epsilon from the received signal model. And so this is h of y, and epsilon is independent of x. The noise and the symbol are independent. Okay, and so this is h of y minus h of epsilon, and epsilon is Gaussian, and so again you can evaluate and find its entropy, and it will be this. Okay, so the mutual information between x and y is equal to h of y minus log 2 by e, like this. And let's see, is the variance of y constrained? So you can compute the variance of y. The variance of y will be SNR, the variance of x, which is 1, plus the variance of epsilon, which is 1. So once you fix the SNR, right? So you operate your system at a given signal to noise ratio by adjusting the transmit power and and so on. Then the variance of y is given. It's given. It's fixed by your SNR. The operating signal to noise ratio. So if you want to maximize the mutual information between x and y, if you want y to reveal more and more about x, now given our derivation here, basically the mutual information between x and y is the entropy of y minus basically this constant. And y is, it's a variance. Its a variance is just a given number, given the operating signal to noise ratio. So the mutual information between x and y is maximized. Okay, if what? What should be the distribution of y such that basically we get the maximum h of y, and hence the maximum mutual information between x and y. The proof on the previous page, it must be Gaussian. Okay, it must be Gaussian. Okay, so basically this is the optimal solution, that y must be Gaussian. So the output of the channel must be Gaussian. And you can show using the characteristic function that now if this guy is Gaussian and x and epsilon are independent and epsilon is Gaussian, then x should be Gaussian. then X should be Gaussian. Then what you transmit on the channel, should basically be Gaussian random variables. If you want to maximize the mutual information. Okay, so we transmit Gaussian signals. So information theoretically, if you want, what should you transmit on the channel? The answer is not binary PSK or 16 QAM or anything. Basically what you should transmit is Gaussian signals. Basically taken from the Gaussian distribution. Okay, so that's really like in many papers you find this thing, Gaussian signaling or Gaussian code books. So the idea is that you will have a binary message, okay, and then this binary message will choose a code word, okay, to select a code word, okay, to be transmitted. So here on the channel there will be a code word, and information theoretically the code word is made up of IID Gaussian samples. If we are interested in maximizing the mutual information. Okay, and in that case, what will be the maximum mutual information? Okay, so now we know that Y should be Gaussian, okay, and so we can plug in the, we know the entropy of Y will be basically the logarithm of this thing here, and you get your very famous expression, the log 1 plus SNR expression that you know from previous course on communications, right? That's the capacity of the AWGN channel. Okay, so you get it via Gaussian signaling. You get it via using the use of Gaussian signals. And of course, in practice, we do not do so. So in practice, this is not what we do. Okay, in practice, the code words are also made of bits, and then we use things like the QAM or other constellations, and then we perhaps will use OFDM, which involves Fourier transform. But in theory, we use Gaussian code books that are composed of code words. The code words are not binary. The code words are composed of Gaussian samples. Okay. Now, what if you have a feeding channel with receive CSI? So the term CSI, channel state information. So for basically the purpose of this course, if I say receive CSI, it means a scenario in which basically the receiver knows the channel. And so practically speaking, it means that the receiver will estimate the channel as we did in the previous lecture, and then use the estimates to basically to guess the transmitted symbol or code word. Okay, so in the case of a receive CSI, you can basically do something like above. I will just give you the final result. The final result is exactly like this log 2 1 plus SNR term. Okay, but now the difference is that you have this channel. You have this H here, which is the channel. So it turns out again, you can basically go through these lines, which like resembles much what we did here. The only thing that you end up with this log 2 plus SNR, but you will have to take expectation with respect to H. So it's something like what we did for probability of error, like compute the probability of error given H and then average over H. So the fading channel capacity is something that is very similar. So the log 2 1 plus SNR expression. Now if there is a fading channel, then basically the instantaneous SNR. So remember this thing. This is the instantaneous SNR, instantaneous S signal to noise ratio. Now fixing H. It's like having an AWGN channel with the capacity log 2 1 plus SNR magnitude H squared. Well, H, if we are interested in an average performance, because H is really basically a random process, then you take the expectation with respect to H. Okay, so these two formulas are very important. Okay, so here and this one. and you take expectation with respect to it, when you implement this expectation, it may be the easiest way to go is actually to use the distribution of magnitude h squared. Okay, but you can write here h or magnitude h squared, and depending on convenience. Okay, all of them are the same. Okay, so welcome, basically to the log 1 plus S and R expression, and hence we have the concept of the capacity. Capacity is the maximum transmission rate, and it is measured in bits per channel use. As you know from your previous course in digital communications, it is the maximum or the supremum of mutual information, and it is basically, you cannot just say the maximum transmission rate. This in and of itself is like sort of meaningless. It's the maximum transmission rate. It's the maximum transmission rate that guarantees that you can reduce the probability of error in the receiver to any arbitrary small level. To any arbitrary small level. Okay? So to prove this, you need to do something called the achievability proof. Achievability proof. So achievability proof means that we can, using a certain coding scheme, make BE as small as we wish. Okay? So you can show that if so basically this capacity will give you a number. It will give you a number, right? And basically if you operate on your channel with a number less than this, so if your actual transmission rate is less than this number, okay, then you can show, and this is like a big and a fundamental proof in information theory, you can show that you can crush the average probability of error to any small value of your choice. And the cost of doing this is that you will use code words that are very long. Okay, so when you do these proofs, I don't know whether you have seen them or not, but typically in an achievability proof, we take the limit as the number of the length of the code word tends to infinity. In this lecture, the last part, I will just focus on the so-called the converse. So I will show you that if you try to exceed this capacity, so this is the capacity, okay? So this is C. If you try to transmit with a rate higher than this value, you are doomed. The probability of error will never be made small, okay? So again, let's basically do this converse in information theory, again, to show that if you obey this rate, you can reduce the probability of error to any arbitrary epsilon greater than 0. It's called achievability. Now for converse, and actually, we will go for the weak converse, okay, which is like sort of easier to prove. So this is very important because this concept I will use a lot in this course. If the transmission rate exceeds the capacity, okay, if the transmission rate exceeds the capacity, okay, then there is no reliable transmission that is possible. In other words, you will not be able. So here, if the transmission rate, your received signal, I will not say it's garbage. It's like not a technical term. It's undecodable. Undecodable. You will not be able to get anything at the receiver. Okay. So it turns out that this quantity that we measured, which is the maximum or maximum mutual information, which is C, it turns out that again it plays this very nice role that if your actual rate is below it, you are very fine and you can enjoy a small probability of error. If you go higher than it, you are doomed. Okay, so how can we show something like this? So let R be the transmission rate in information bits per channel use. So basically here, what we saw, we have code words that of n samples. So here our code word, okay, each code word has n samples. And so when you transmit the code word, you use the channel n times. We say n uses, okay? Because like each sample, so you basically transmit a sample followed by sample followed by sample and so on, okay? And so the code word constitutes n uses of the channel. Okay, so it's okay. So basically, your code word is one of many code words that are possible. Okay, so you have a code book, and you select a code word based on a message. Okay, so again, the way to do it is that you have a code book, and you enter here NR. Okay, so basically this is N, the length of the code word, and R is basically the so-called information rate. So you have message, NR bits, to use or to select one of 2 to the NR code words, and those are to be transmitted to the code word to the channel. Okay, and so perhaps like in a previous course, like you called this NRK or something like this, right? So typically in some reference words that use K, and then they will define K over N as the coding rate. Okay, I mean, just make sure. I am sure that you took part on coding like in 242. Is this correct?
Yes.
Yes. Okay. So yeah. Okay. So here I will just use this notation that basically you have code words of length n, and then you have nr is the number of bits to use basically to select one of the code words. Here we are very abstract. We don't care about how those code words are. In fact, when Shannon developed the information theory, actually his code book was random, which means that you generate the code words by simply generating Gaussian samples. Okay. The trick actually is how to do something in practice that gives you the same effect. Okay, so that's challenging, but like theoretically speaking, this code book can be like even generated randomly. Okay, and so here's our system. So our system is that you have a binary message, and you use the binary message to select a code word of length n. So it has n samples, and then you put this thing on the channel. You get n received samples. So what is the relation between the y's and the x's? Oh, basically you have the contamination by the Gaussian noise, and then in the receiver you get your received code word, and you apply a function to it to make it guess which code word has been transmitted. Okay. So now let's measure the mutual information between W. Okay, so basically our code word is what is on the channel, but actually it is selected using a binary message. So the mutual information between W and Y, again by definition, it is the entropy of W minus entropy of W given Y. So basically move this term to the other side. Okay. And actually switch the terms. Actually, so basically we have h of w y n is equal to h sorry, yeah, we'll move it to the other side. So we'll have h of w is equal to the mutual information plus h of w given yn. Okay, so what is the mutual information of w? Assuming equal probable code words, then from the first slide on this lecture, basically we know that if you have equal probable code words, okay, it's like having the discrete uniform distribution. Basically, the entropy will be log to the base 2, and then the number of code words, and so this will give you nr. Now, what about these two terms? Well, we will upper bound each one of them. Okay, so for this one, we will employ the data processing inequality. The mutual information between this and this, okay, is, because we have like two channels in the way, is basically less than or equal to the mutual information between x and y. Now you can show from the definition of mutual information that if you have a sequence of random variables and another sequence of random variables, okay, then again under some conditions you can show that actually this mutual information is the sum of the mutual information between each x and each y. Now this mutual information here by definition is upper bounded by C, which is by definition is the maximum. And so basically the mutual information between the transmitted code word and the received code word is upper bounded by NC. What about the other term? What about this term here? Okay, so let's define Bernoulli random variable E, which is 1 if you have an error, which is 0 if you don't have an error. Okay, so you apply your function G to the received code word. If you get W, if you get the true code word that has been used to select the transmitted code word at the transmit side, you are good and E is equal to 0. Otherwise, E is equal to 1. Okay, so what is H of W given Y? So here is the trick. H of W given Y is H of W given Y, and then I will add this extra term. H of E given W and Y. So this is 0. Why is this 0? Think about it. You know Y, right? If you know Y, you will apply the function G to it. Okay, so apply G to Y to know the estimate for the transmitted code word. Knowing W and W hat, we know whether E is 0 or 1. So the E again is a Bernoulli random variable telling you whether you get it right or not. Now, if you know W, conditioned on W and Y, well, you know E, because Y, you will apply some deterministic function to Y to get the estimate W hat, and then you can compare W and W hat. If they are the same, E is 0. If they are different, then E is 1, and you are done. So this is 0. Okay, so here is the thing. So basically you have given Y, you have here H of W, and here H of E given W. And so these can be written in terms of the joint, and then you can rewrite the joint in a different way. Remember, we have this trick here that H of AB is H of A plus H of B given A, and also it is H of B plus H of A given B. So the trick here is to insert this 0, write things in terms of a joint, and then rewrite things as of H of E given Y plus H of W given E and Y. Okay. What is H of E given Y? Well, this entropy is upper bounded by H of E, and E is a Bernoulli random variable. So what is the maximum? So a discrete random variable that can take one of two values. What is a maximum on an upper bound on its entropy? Log 2 to the base 2, which is 1. Okay, so this term here can be upper bounded by 1. What about this guy? This guy is a bit tricky. You know, so here it tells you what is the uncertainty about W if we know E and if we know Y. Okay, let's take this. Because E is Bernoulli, we can basically investigate the two cases. Okay, and so we can take this guy and say, well, we can say E is 0, and we multiply here by the probability of 0, or perhaps E is 1, and we multiply here by the probability that E is equal to 1. Okay, now, let's look at this entropy. I'm claiming that it is 0. Why? We know Y. Okay, so knowing Y, from Y you can compute what? From Y you can compute W hat, right? So from Y you can compute W hat. And knowing that E is equal to 0, then you know that there is no error. So W is equal to W hat. Okay, so the entropy is 0, right? So G of Y gives you W hat. You know that E is 0. Then do you know W? Exactly. We know it exactly because we know that the error is 0, and we can compute, and so W is W hat, and we can obtain W hat by basically applying the function to Y. So this is 0. Last term. So what if you know that there is an error? Now, you get G of Y is equal to W hat. So, and E is 1. So what do you know about W? So W is any code word other than what? W hat, right? Because so if E is 1, it means that you are conditioning on the event there is an error. So there is an error, it means that the transmitted code word W is different from what you have at the receiver W hat. But which one of them? Which one of them? Okay, because in total we have 2 to the n are code words. Okay, exclude W hat, then we have 2 to the r minus 1 code words. Okay, so W is any one of those, and the entropy is maximized. I mean, so basically you may say, well, I can upper bound the entropy of W given that E is 1 and Y by basically the log 2 of the number of the other code words, 2 to the NR minus 1. Okay, and then you can remove the minus 1 as an upper bounding step, and this will give you to NRPE. Okay, and so you get this very nice inequality. And this nice inequality can be manipulated and written as this one, which is the last thing I will say here. The probability of error in our system is greater than or equal to 1 minus C over R. You may look at this and say, then what? So we have a lower bound on the probability of error. If R exceeds C, then BE cannot be made 0. Okay, so basically that's the so-called weak converse. And the strong converse is actually that if R exceeds C, the probability of error becomes really bad. You know, it's not, you know, that, you know, perhaps you say, okay, so the probability of error, you know, maybe it's like greater than or equal to 10 to the minus 12. I mean, this will be like, you know, a very acceptable probability of error. No, things are actually worse. It's like, again, for the purposes of this course, if you exceed C, your bucket becomes undecodable. It becomes useless. We will just throw it away, discard it. Okay, unless we apply diversity technique, as we'll see later. Okay, so C is a fundamental quantity in wireless communication and in communications, even on wires. Okay, it's not just something for wireless, and it is sort of a magical quantity that you need to obey for reliable communications. Okay, and we will start applying these concepts in the